Welcome back. This is part 2 of section 1.3, and we'll continue talking about samples and experiments, and we'll start with some definitions involving observational studies. So remember that an observational study is when you just observe something and you're not modifying it in any way to record the results. We're just observing something either in the wild, but in particular, we're not affecting what it is we're studying. So there are three types here. So retrospective, cross-sectional, and prospective. So retrospective, as the name implies, is going to be reviewing data that came from the past. So maybe older records of, say, weather patterns from hundreds of years ago, using this to look at something, older interviews, but essentially it's data that was collected in the past. Cross-sectional data is data that comes from exactly one point in time. And if you're doing an observational study that's going to be cross-sectional, something like this might be looking at maybe all the weather patterns across Earth, but on a given day. Or you have one expedition into the jungle to count how many monkeys you see. So cross-sectional is data that's coming from exactly one point in time. But we can also go forward in time with prospective data. And this is data that's sort of worded in the way that this is coming from the future. But what's more apt here is that this is data that's collected from a group that has shared some factor from some point in time onward. So a good example of this might be studying people that began smoking at a certain age versus people that have not smoked. When you're doing this, I might set up a study now to study the smokers in the future, or the non-smokers in the future, and I don't have that data now, but at the end of the study, say in 10 years, I can collect that data. So the perspective here is that this is coming from the future, but it's more like we just start a study, and then in the future we'll collect that data. Once a sample is collected, then you can begin to look at the actual experiment yourself. So this is moving away from observational studies back to experiments. And when you have an experiment, it is important to have different treatment groups. So for instance, if you're studying the effect of medicine on a group of people, you not only want to give some people the medicine to observe the results, but you also want to know what happens if you don't give people that medicine. So you'll have a placebo group. Or maybe the treatment group will be split further into people that receive some amount of treatment. So maybe you have one group receive so much treatment, and another group receives double of the same amount of medicine. So you can have more than just two groups, as in a placebo and a treatment. The treatment can be split up further. So how you divide the people into the different treatment groups is equally as important as selecting the sample, selecting the group of people to study. So we're going to assume that we have a sample of people now. And then the question is, how do we separate those people into different treatment groups? And these will seem very similar to how we selected the samples. The first one is just completely randomized. So we will assign people to the different treatment groups in an absolutely random fashion, usually aiming to keep the different treatment groups about the same size. Now, if we wanted to interfere in exactly this randomness, and there are reasons for this, we could use a random block design. So this is a lot like the strata that we had before, the stratified sampling method, where maybe there are some factors that we want to sort of eliminate their effects in our experiment. Say we're doing a medical experiment on men and women. It would not be a good experiment design to give all of the men the treatment and all the women the placebo, or vice versa. What would be better would be to choose a random sample, to choose a random block from the men and a random block from the women to get the treatment, and a random block from the men and women to receive the placebo. This will make sure that we're not accidentally seeing effects from being men and women rather than the treatment versus the placebo effect. So this is random block design, very similar to the stratified sampling method from before. Another way is matched pair design. So the matched pair design, so there's two common ways to do this, but essentially what we're doing is you pair 2 points of data, or two subjects, and you're looking at the difference between these. So one way to do this is you have before and after comparisons. So maybe you collect some data on the first of the year, and then you collect some data at the end of the year, and then this data is going to be paired. One person will be tested at the beginning of the year and the end of the year, so you can compare those two. So one of your groups, one of your treatment groups, might be the data from the beginning of the year, and the other treatment group, maybe this is the after the treatment has been given, would be from the end of the year. Or you can pair similar subjects. So say we're looking at medicine's effect on some health issue. One thing that we can do is we can go through our sample and we can pair up individual people that are maybe roughly the same age, have the same backgrounds, the same sort of external factors like smoking or their active lifestyle. And by pairing these similar people and putting one in the treatment group and one in the placebo group, for instance, would mean that any factor that might affect this is being mitigated. Any factor that might affect our results is being mitigated by having similar people in both the treatment and non-treatment groups. And then lastly, just the rigorously controlled design. A lot like we said before, this is just going through and individually choosing who gets which treatment to try to do everything to the best of our ability to make sure that no confounding occurs, to make sure that no factors will affect the different groups in different ways. This is usually a little bit time-consuming, but if this could be done very quickly, it would be a very, very good option. And I mentioned the word confounding. Confounding is when the factor causing an effect can't be determined. Maybe we want to look at how a treatment affects people, but the group that received the treatment were all white, and the group that didn't receive the treatment were all black. This could confound the results, meaning that we don't know if it was the treatment that was having the effect, or if their background was really having that effect. And some other sort of common errors that can happen, as in we do our analysis, we get some results, but they don't seem correct. Where could they have come from? So one thing is from sampling errors. It could be that even though you had the perfect method for choosing a perfectly random sample, you could have accidentally randomly chosen 500 women to be in your sample, in which case it's not representative of the population being roughly split. So a sampling error is just when you selected a bad sample. A non-sampling error is an error that comes from something other than the subjects in the experiment. So it could be someone enters a number in wrong, or you make some sort of computation in the wrong way. It could be that the people reporting the data lied to you. There could be some bias coming out somewhere. Non-sampling errors just come from anything. That's not just how you chose the sample. And then the last one, the non-random sampling error versus the sampling error. Sampling error is when the sample was chosen randomly, but just happened to be just unlucky, got a bad sample. A non-random sampling error is when your sampling method was bad. For instance, the convenience sampling method, where you just choose the easiest sample that you can choose. Quite often, it won't be random, and that was because it was a poor sampling method. Or maybe you use the cluster sampling method, where you chose a group of people, you chose a cluster of people to test randomly, but people within that cluster all had some characteristic that confounds the experiment. So non-random sampling error would come from just having a bad sampling method, as opposed to just getting unlucky with your random sample.